This. Okay.
Max, should we start?
Yeah, fine with me.
So we're honored to have Professor Ramon van Handel from Princeton. He has solved several important conjectures in probability, functional analysis, and convex geometry. Among many accolades, he's won the NSF Career Award as well as the Erling Prize, and we're very happy to hear him speak today about the diabolical bubbles of Minkowski, Alexandrov-Fenchel.
Thanks, Howie. It's a real pleasure to give the colloquium here, and yeah, I want to tell you about the project. Everything I'm going to talk about is joint work with Yair Shenfeld, and we had a lot of fun with this over several years, and I will try to convince you that there's some interesting phenomena here, and that there's interesting things to be studied. So let's start with something that everybody knows. Here you have my son Benjamin is demonstrating for us the classical isoperimetric theorem. So we all know this from when we were very young, right? If you have a body, right, a set with a fixed volume, and you want to know which set with the fixed volume has minimal surface area, well, this is of course the ball, which is why soap bubbles are around, right? Because there's a fixed volume of air trapped inside, and the soap film is trying to minimize the surface area, and it becomes a beautiful round ball, right? So the ball is the unique minimizer of the surface area with fixed volume. Now I put here convex between brackets because of course the classical isoperimetric theorem doesn't require convexity, right? But this is a talk about convex geometry, and in this talk all of the sets I'm going to talk about are going to be convex. Okay, so I'm just saying this up front, and we will take it for granted from now. So this theorem is very classical. I mean, it's known to every child who's blown a soap bubble. You know, it involves two geometric parameters of convex bodies, volume and surface area. And why would you just think about these two parameters, right? I mean, these are just two of the many geometric parameters associated to convex bodies. So, you know, it's a really natural question to ask is what happens if we introduce some other geometric parameters of convex bodies and we fix those too? And then let's ask the same question. So let me give you an example. And this is probably the oldest example of this kind of phenomenon. Let's think, in addition to a volume and surface area, about the mean width of a body, right? So I've just drawn here a picture of what this is, right? So if I have a convex body K, and right, so here's a convex body K, and I fix a direction X, right? Fix a direction X, then I can always take two hyperplanes that touch the bodies with that normal direction that touch the bodies on both sides, right? And the distance between those two hyperplanes is the width of the body in the direction X, right? So just imagine if I give you a convex body, you take calipers and you're going to measure the width of the body in a certain direction just by taking the calipers and pushing them against the body. And if you average the width over all possible directions, then you get the mean width of a convex body, right? So this is a perfectly respectable geometric parameter of convex bodies, just like volume and just like surface area, right? So, you know, let's now ask the same question as we did before. So we take all bodies with fixed volume, let's say volume 1. But now we're also going to fix their mean width to be some parameter, some other number. You pick whatever you want, right? And now among all of the bodies with fixed volume and fixed mean width, two given values, now which one minimizes surface area? It's the same question as before, but we fix one more geometric parameter. Now, of course, if the value of the mean width you pick is the mean width of a ball with the given volume, right? So if we fix the volume to be 1, and we fix the mean width to be the mean width of a ball with volume 1, right? Then of course the solution is the same as the classical isoperimetric problem. But if you take a different value of the mean width, then the ball can no longer be a minimizer. For example, right? If I fix the volume to be 1, but I fix the mean width to be larger, strictly larger than the mean width of a ball of volume 1, right? Then the ball can no longer be the minimizer because I'm forcing my bodies to be wider than they want to be. And if you do this, the question is now, you know, if I force my body to be wider than it wants to be, what is now going to be the minimizer of the surface area, right? It can no longer be a ball because the body has to stick out, right? It has to stick out because it needs to be wider than a ball, right? So, you know, unfortunately, Zoom is not a very good mechanism for me. You know, if I were sitting with you in a room, I would look everybody in the eyes and ask them, what do you think? We do a little poll. You know, from experience, I know that most people guess that the answer is an ellipse, right? An ellipsoid, which is a perfectly respectable. It looks like a ball, but it's a little bit wider, right? And I've heard various other guesses over the years, but none of those guesses are what actually happens, at least the ones that I've encountered. What turns out to happen is very strange, and I will show you a picture. Here it is. This is the so-called cap body. Okay, so what have we done? We've taken a ball and we've added some spikes to it. Here's a spike, there's a spike, here's a spike. So the way that these bodies are generated, here I can draw it in the corner here, is that you start with a ball and you take a point outside the ball and you take its convex hull with the ball, and then you get a cap that sits on top of the ball. And you can do it again. For example, you can take a point over here and take the convex hull of a ball, and then you get another cap that sits on top of the ball. And I can take another point over here, and I can take the convex hull, and then I get another cap that sits on top of the ball, right? These caps are like party hats, like you put on your head, right? And you can put as many of these caps on as you want, as long as these caps don't overlap with each other. And then you have something called the cap body of the ball. And these are very strange objects, and it turns out that this is the most efficient way of minimizing surface area when I'm forcing my body to be wider than the body wants to be. The most efficient way to minimize surface area but make the body wider is to have these spikes sticking out of it. From the point of view of isoperimetric theorems, this is a very, very strange phenomenon, okay? Because, you know, if you have ever studied classical variational, variational approach to isoperimetric theorems, the solutions have many, standard properties. For example, they tend to be very smooth. They tend to have constant curvature. They tend to be unique, right? This is a situation where exactly the opposite happens. You see, the optimal bodies are not smooth at all because they have these points sticking out of them. They're highly non-unique because you can move around, for example, where the caps are on the surface of the ball. You can add more caps if you want. You can add as many caps as you want. And you can do this in infinitely many ways and achieve the same volume and mean width, right? So it's highly non-unique. It's highly non-smooth. So as soon as you depart sort of from this classical story about isoperimetric theorems, suddenly you have these very strange phenomena that show up. Right? So these are very strange objects. And, to me, they really capture my imagination. It means that if the laws of physics had been such that there was some sort of, dark force, right, that forced soap bubbles to be wider than they want to be, right, then our soap bubbles would look like these little diabolical bubbles with horns sticking out of them, right? And not only would they look like that, but they would be constantly, these caps would be constantly scintillating like this because, there's infinitely many of them that give the same volume and mean width. So they would be highly unstable, right? They would be shimmering, right? So that's a very strange world that we would live in if that were the case. Of course, the physical world is not like that, but in the mathematical world, is much more beautiful. So good. This is a very old, this is perhaps the first example. It's very old. It dates back to Minkowski's original paper in 1903. This is one of the very first papers in the area of convex geometry. And Minkowski conjectured that these are, that this is the solution, this is the solution to this problem. He showed that this is a solution to this problem. And Bohl, 40 years later, showed that these are the only solutions to the problem at the previous, okay? But this, what I want to convince you in the rest of the talk is that this is just one example of a much more general phenomenon. And I will try to explain what is the theory that lies underneath this, this example. And I will also try to show you that these objects, these very strange objects, show up in many unexpected places, or at least in one unexpected place. And I think they should show up in many more unexpected places. So that is my goal for this talk, and that's where we go. So, okay, so let's talk a little bit. We need to talk about what lies, what is the basic objects that lie behind this example. The first thing we need to discuss is the notion of addition of convex bodies, right? So if I have two convex bodies, K and L, K and L, these are two convex bodies, and I have two numbers, lambda and mu, which we will always take to be non-negative. I can simply add up the two convex bodies, right? Or take a linear combination of two convex bodies. It just means that taking linear combination of any choice of points in those two bodies. Of course, this definition makes sense even if K and L are not convex, right? It shows up in many different places. For example, even in number theory, you have in additive combinatorics, you have these type of constructions. But if K and L are convex, then this linear combination will also be convex. You get again a convex set. Okay. So here is an example. So let's take a square. We'll call it K. And for me, B will always be the Euclidean ball in whatever dimension I'm working in. So here we're in dimension 2. Let's take a square K. Let's take a Euclidean ball of radius 1, but multiplied by epsilon. Right? Then it will be a Euclidean ball of radius epsilon. So how do you add them up? Well, I have to take every point in K and add to it all points in epsilon B. So all you have to do is you take this ball and you center it at every point in K, and you shift it all around K and take the union of all those sets, right? And what you get is exactly this object over here with these rounded corners, right? Because, for example, here over here, there was one of these balls, and here is another one of these balls, etc., right? And when I shifted the ball over the entire set K and added all of them up, I get exactly this Minkowski. Okay, so here is one example of this situation. And this simple example is already showing us the basic property that we're going to talk about. So let's compute the volume of this sum. Right? So if you look at this picture, you see that inside you still have the original set K. Right? So the volume is the volume of K. Now, along every edge of this of the original set K, if I scan a ball over it, I get this rectangle. And this rectangle has volume. It has width epsilon, which is the radius of the ball. So the volume of this rectangle is exactly epsilon times the length of that edge. So if I sum up the volumes of these three rectangles, right, I get exactly epsilon times the sum of the lengths of the edges of the square K, which is exactly the surface area of K. So these rectangles give me epsilon times the surface area of K. And what are left are these little pi wedges over here. Right? I have 4 of them, but each one of them is exactly 1/4 of the ball of radius epsilon. So when you add them up, I get exactly the volume of a ball of a radius epsilon, which is epsilon squared times the volume of K. So what you see in this picture, in this one example, is a very basic fact, which is that the volume of the Minkowski sum is actually a polynomial. You see, it's a polynomial of degree 2 in epsilon, in the radius of the ball, which is something that's not obvious a priori if you first think about this, but this is always true. Right? So, this is a general fact, and let me write it out. I see there's a lot of things in the chat, but everybody is perfectly welcome to answer questions, but please unmute yourself and speak up because I will not see it in the chat if you have questions. So I'll go on for now, but anybody is free to interrupt me with questions.
So can I ask?
Of course, yes, please. Yes.
Another definition. So lambda and mu can be any 2 positive numbers?
Well, I mean, you could define it that way, but I'm going to think of lambda and mu as being non-negative. And, okay, this definition makes sense for lambda and mu being any real numbers. But you see, this volume is not going to be a polynomial if you take epsilon to be negative.
Yes.
Also, right? Because minus epsilon b is just epsilon b, because b is symmetric. Does it make sense?
Yes, but my question is more about like if I take mu times something in epsilon b and mu is very, very big, I can get, I think, any point in the plane, right?
Sure. If you take a ball of radius epsilon, you let epsilon go to infinity, you get the whole plane.
Or even if I take the mu to be very, very big, not the epsilon. Epsilon is fixed, but I take mu times.
No. Here I took epsilon to be mu and lambda to be 1, right?
Ah.
I took mu to be epsilon and L to be b.
Okay.
Of course, you can, you could take mu to be 1 and L to be epsilon b, but okay. Mm-hmm. We're thinking about this as a function of epsilon. It'll become more clear on the next slide.
Okay, thank you.
But for me, if you see these combinations, I'm always going to take them to be non-negative, okay? Because when you go negative, there is some, there's some asymmetry in the way that this definition is defined. Okay, are there any more questions? All right. So, here it is. I'll emphasize this point again about the previous question. So the point is that volume is actually a polynomial of convex bodies. Right? right, with respect to Minkowski addition. So what does it mean? Let's take any convex bodies in Rn. Yes, please.
Sorry if I can just add something. So
yes.
Usually if you deal with convex bodies which are invariant under taking minus, then you may just as well reduce to using positive lambda and mu, right?
Well, the point I was let's look at this example, right? The point I was trying to make is that if you make epsilon negative, you still have this representation, but now you get here the absolute value of epsilon.
Right.
And then it's no longer a polynomial in epsilon.
Right.
Does that make sense?
Yeah.
So it's a polynomial if you restrict to non-negative weights. Right? This is the.
Yeah, and just try to point out that if k and L are invariant, like if k is the same as minus k and L is the same as minus L, then you may just as well like take positive lambda and mu, because if they're negative, then it's the same thing, right? It's the same set, like minus lambda k is the same as lambda k if k is minus k invariant. Yeah.
Well, it depends on what you're trying to do, right? But I'm just trying to point out that you should be careful that when I write down formulas like this and they look like polynomials, right? Yep. They are only polynomials when you restrict to non-negative weights. And if you were to allow negative weights, of course, everything is well defined. And because here in this example, the bodies are symmetric, you get exactly the same formula. But now you have to take the absolute value and it's no longer a polynomial, right? It will only be a polynomial in the absolute values of the coefficients if the bodies are symmetric. And if the bodies are non-symmetric, then it will look different when some of the coefficients are negative or positive.
Thank you.
Okay, yeah, all right. So let's go back. So volume is a polynomial. Again, you have to be careful. It's a polynomial for restricted non-negative weights, right? So if I take any family of convex bodies in Rn and I take non-negative weights, and I take the volume of the linear combination of these bodies, right? So I could take any m bodies in Rn. And it turns out that this is always a homogeneous polynomial of degree n in the dimension of the weights, right? So we say that the volume is a polynomial as a function of the convex bodies. And this polynomial has some coefficients which depend on the bodies that I stuck in. And those coefficients are called mixed volumes. Okay? And, once you have this insight, first of all, for example, on the previous slide, you saw some examples of mixed volumes. So the volume is a mixed volume. The surface area is also a mixed volume, right? So these are very natural geometric parameters. And in any dimension, you have such representation. So for example, if I so in n dimensions, the mixed volume is a function of n convex bodies. If I plug in the same body for all of them, I get the volume. But if I replace one of them by the ball, I get something proportional to surface area. If I take all of them except for one to be a ball, then I get something that's proportional to the mean width, which we've already encountered, right? But of course, I can plug any combination of bodies into these mixed volumes and I get all sorts of different objects. But you should think about these objects as being very natural geometric parameters associated to convex bodies, right? So once you know that volume is a polynomial, it's natural to study the coefficients of that polynomial. And you should think about these coefficients as being an extremely general family of geometric parameters associated to convex bodies, of which volume, surface area, and mean width are just 3 examples, right? This is really the viewpoint that was discovered by Minkowski in this paper from 1903. Now, these coefficients have some very basic properties. The most non-obvious one is that they're always non-negative, right? These are geometric parameters, so they're non-negative. This is not obvious that you have a polynomial that has to have non-negative coefficients. The other 3 here are obvious. They're symmetric in the sense that if you permute the bodies that you stick in, you get the same thing. This is by definition, because this is the coefficient of this monomial, which is symmetric. So you might as well take them to be symmetric. They're linear as a function of each of the convex bodies. This also follows directly from this representation. And if I translate any of these bodies, then they're also invariant. This follows from the fact that volume is translation invariant, right? If I shift the set, it doesn't change the volume. So, these properties, they're not so, I'm not going to use them explicitly, but I sort of take them for granted. So I just mentioned them at the outset. So, this is a basic fact, right? So what you should remember is that volume is a polynomial, and you can think of the coefficients of that polynomial as being the family of natural geometric parameters associated with a convex body. And Minkowski, his idea was, once you understand that, then of course, if you want to prove things about geometry, you should look for theorems about these coefficients. For example, you should try to find inequalities between these coefficients. And probably the most basic and fundamental inequality of this kind is called the Alexandrov-Fenchel inequality. Actually, this inequality was already proved by Minkowski in dimension 3, right? So it should really be called Minkowski Alexandrov-Fenchel, I guess. So in dimension 3, it's due to Minkowski 2 and 3. In higher dimensions, Minkowski's proof doesn't give you the general case; it only gives you a special case. And in the 30s, Alexandrov proved this theorem in complete generality. And oops, where are we going? What does it say? If I take the mixed volume of n convex bodies in Rn, KL and n minus 2 reference bodies, and I square it, it's greater or equal than the same thing with KK and LL. So you should think of these n minus 2 bodies are being fixed. And what I vary are the first 2 bodies. Here I have KL squared, here I have KK, and I have LL. So this looks exactly like the Cauchy-Schwarz inequality, right? The inner product between x and y squared is less or equal to inner product between x and x times the inner product between y and y, except that the inequality sign is reversed. So this is a so-called hyperbolic inequality. And this turns out to be a very general inequality. You can combine many instances of these inequalities to get more complicated inequalities for mixed volumes. And many of the geometric inequalities that are known in convex geometry follow as special cases of this inequality. So this is a very fundamental fact. And already from the very beginning of the theory, very early on, the question was asked, for which bodies do you actually get equality in this inequality? And this question really dates back to the original paper of Minkowski in 1901. And let's think for a little bit about what is the significance of this question. So let me just give you a very simple example. So this example is in dimension 3. So in dimension 3, mixed volume is a function of 3 convex bodies. And I'm just plugging in 3 special bodies. The ball will be the first one. I'll take a body K to be the second one, and I'll take the same body K to be one of the reference bodies. Okay. So in that instance, you get this inequality, VBKK squared, right, is V greater than VBBK times VKKK. And if you remember on the previous slide, these particular examples of mixed volumes were very familiar because this guy over here is proportional to surface area. This one is proportional to mean width, and this is just the volume of K. So this is a geometric inequality involving 3 parameters: surface area, mean width, and volume. Right? And those are exactly the parameters that I started with on one of the first. So now let's ask the question that we asked before. Suppose that I fix the volume to be a certain value, and I fix the mean width to be a certain value. Which convex bodies minimize surface area? Well, if I fix the volume to be a certain value, and I fix the mean width to be a certain value, then I fix the right-hand side of this inequality. Right? And so now the left-hand side is just surface area, right? So if I fix the right-hand side, and I want to know which body minimizes the left-hand side, well, if this is a sharp inequality, that body will be exactly the body that attains equality in this inequality. So you should really think of this inequality as being a kind of isoperimetric inequality. And the question about equality cases is exactly the question about which bodies minimize the left-hand side, given that you fix the quantities on the right-hand side. That's the isoperimetric theorem. And in fact, what Minkowski and Bohl proved is that equality in this inequality holds if and only if K is a cap body. And that theorem, right, the characterization of the equality case, is exactly what gives rise to that picture that we saw over here, right? This picture that we saw over here, the solution of this very strange isoperimetric problem, is exactly equivalent to the characterization of the equality case in this very special case of the Alexandrov-Fenchel. So the point here is that equality cases of the Alexandrov-Fenchel inequality are equivalent to understanding certain extremal problems associated with convex bodies when the parameters that you're fixing in your extremal problem are mixed volumes, as opposed to just volume and surface area will be mixed volumes, right? Which are much larger class of geometric parameters. And this is the idea. So this question is old. It dates back to the original papers of Minkowski and Alexandrov very early on. Until recently, the answers were known only in very special cases. So Bohl and Minkowski proved it in this very special example that I wrote here on the previous slide, this one. This is just for very specific choices of the convex bodies. But the method of proof used there are very special. They use some geometric construction that is very special to this case, and it fundamentally cannot address the more general problem. And for a long time, there were really no methods to prove things about this question. In fact, for a long time, there weren't even conjectures. It is known that there are many, many equality cases, but how could you even characterize them? Until the 1980s, when Schneider proposed some really fundamental conjectures in this area. I think without those conjectures, it would have been impossible to do anything. So, and those conjectures have been proved in very limited cases using special methods. But it's very hard to address this problem, in complete generality without developing new ideas. Maybe let me say a word about why this doesn't follow from the inequality, right? Usually when you have an inequality and you want to understand its cases of equality, right? All you have to do is study the proof of the inequality and look every time that you make an inequality in the proof of the inequality, what would happen in that step if you had equality. And then, you trace this through the proof and you end up with a characterization of the equality cases. So it turns out that this is fundamentally, that doesn't work. And the reason it doesn't work is that the proof of the Alexandrov-Fenchel inequality, all the known proofs really work by approximation. What you do is you first prove the inequality, for example, for smooth convex bodies, or for certain types of polytopes with very, very special assumptions. And it turns out that for those very, very nice convex bodies, you have no interesting equality case, right? So for example, if you think about the cap body of all those spikes, it wasn't smooth, it has all those spikes, right? Well, the proof of the Alexandrov-Fenchel inequality doesn't work for those bodies. It becomes singular. If you plug in those non-trivial equality cases into the proofs of the classical proofs of the Alexandrov-Fenchel inequality, everything becomes singular and the proofs don't work anymore. So the way the proofs work is by approximating the bodies by nice bodies for which there are no interesting equality cases. You prove the inequality, and then you prove the general inequality by taking a limit. But such proofs cannot tell you anything about the equality cases, right? Because the equality cases disappear when you approximate. It's exactly when things become singular that you get interesting equality cases. And so, the singularity really lies at the heart of this problem. So we made a lot of progress on this with Yair. And in particular, we have a complete solution in the case of convex polytopes. This is somehow the combinatorial setting of this problem. And we settled also various other cases, which I'm not going to talk about in this talk. I'm mostly going to talk about polytopes, where we have a complete solution. But there is a lot of progress. The completely general case is still open. And if I have time, I might say just a little bit about it later, but not much.
May I ask a question?
Of course, yes.
Ago? 2 slides
ago.
Yeah, so yeah, the examples here, some of them are proportional. So there is a constant C for the second and third cases. So with those constants, is it still like every time it's going to yield the same kind of inequality?
The constants here only depend on dimension. I was just too lazy to write them out. So for example, the constant here is n, n over here. So 1 over n on the right-hand side, n being the dimension. And here it's another explicit constant depending only on the dimension. So, I was too lazy to write it because it involves some factors of pi and, but these are absolute constants. So they make no difference in the inequalities, right? I mean, they give you the optimal constants in the inequality.
Okay, thanks.
Yeah, this is a good question. So yeah, I mean, I didn't hide any. I mean, I hid something here, but it wasn't something important. Right? So this is, but that's not obvious from the way I wrote it. Are there any more questions? Okay, so before I go on, I want to change gears a little bit, and I want to show you that this type of question, so far these are questions about convex geometry, about extremal problems in convex geometry. But it turns out that these type of questions arise in surprising, there are surprising connections with other areas of mathematics. And I want to give just one example of this, one sort of classical example. But more generally, it turns out that for some reason, which I don't really understand, mixed volumes turn out to be very good at counting things. And, if you put in particular types of convex bodies, you can engineer the mixed volumes to count solutions to certain sets of equations. For example, to sets of polynomial equations, a number of solutions are given by mixed volumes. and they're very good at counting certain type of combinatorial objects. So let me give one type of application of this that is very interesting. Let's first make a classical definition. If I have a sequence of non-negative numbers, usually we will take these to be integers. The sequence is called Logconcave if it satisfies this inequality. Ni squared is greater or equal to ni minus 1 times ni plus 1. So this is the definition of a Logconcave sequence. And you should think of this as a strengthening of the unimodality property. Every Logconcave sequence is unimodal. That means that it first goes up and then it goes down. Right? It cannot go up, down, up, down. Now, it turns out that in combinatorics, there are lots of sequences of, that count things in enumerative combinatorics that turn out to be Logconcave. This seems to be a very general phenomenon, and often for very non-obvious reasons. And there are some long-standing conjectures that things are conjectured to be Logconcave that is not yet known. So the simplest example, of course, is the sequence of binomial coefficients, right, which count the number of ways of choosing I objects out of n, right? One could view this as a combinatorial object, maybe a little bit silly. So binomial coefficients as a function of I from I is 1 to n or 0 to n is a Logconcave sequence. You can just check it by plugging it into this definition. But this is you can just do it by hand. But in other situations, it's not at all clear why things should be Logconcave. So here's a classical example due to Stanley. So this arises in the combinatorics of partially ordered sets. So let's take some set. It consists of n elements, but I have suggestively named one element x and the rest of them y. But I can take any x, okay? So take any partial ordered sets of n elements and identify one of the elements we're going to work with, which call it x. So on this set, we have a partial order, right? We have some order relation, so not every pair of elements are ordered. That would be called a linear order, right? But only some subset of the elements are ordered, right? So they satisfy the axiom of an order. This is a partially ordered set. Now, if I give you any partially ordered set, you can always extend the partial order to a linear order. You can always rank the elements in a partially ordered set in such a way that the ranking is compatible with the partial order, right? And if one element comes before the other in the ranking, right? Then, if one element is less than the other in the partial order, then it comes before them in the ranking. Right? It's very easy to do this. For example, you can start with all of the minimal elements and put them up on the bottom of your ranking, then take all of the next elements and put them next. You just make this greedy construction, and you can always extend the partial order to a linear order. Now, one question you might have is, in how many possible ways can you do this? And the question that Stanley looked at, it was based on a conjecture that appeared earlier in the 70s, is let's take this partially ordered sets with this distinguished element. Let's take this partially ordered set with distinguished element x, and let's count how many ways I can extend this partial order to a complete order, to a linear order, in such a way that this element x comes in rank I, right? So it's the I smallest in the total ordering that I get. So this is a basic question in the combinatorics of partially ordered sets. And this question and also more general questions along the same lines that can be treated using the same theory turn out to have interesting applications, for example, to sorting algorithms. In theoretical computer science, if I give you a set, you might want to know how many pairs do I have to, let's say a set with a total order, but I don't know the total order and I need to sort the set, right? So what I will do is I will just query pairs of points, and the the query will tell me which point is larger than that point. You want to know how many queries you need to make in order to totally sort the set. And it turns out that, so here every time I query a new point, I add a relation to my partial order, and you want to know how often to do this. And to analyze these type of sorting algorithms, it turns out one has to understand this type of combinatorial question. Okay, so this is a basic combinatorial question. And it was conjectured in the 70s that this sequence of numbers, which is a purely combinatorial quantity, is always Logconcave. And it was a conjecture. It wasn't clear how to prove this. And Stanley proved it in the 80s. How did he prove it? Well, what he did is he cooked up some polytopes K and L, such as that he could represent these numbers Ni as the mixed volumes of certain number of copies of K and certain number of copies of L. It's just a construction. Right? You construct some polytopes that are related to the partial order. They're called order polytopes. And if you plug these polytopes into the mixed volume and multiply by some constant factor, you get exactly these quantities. And once you have represented these quantities as mixed volumes, then the Logconcavity is exactly the Alexandrov-Fenchel inequality. This mixed volume squared is greater or equal to what you get if you replace 1k by 2k's and if you replace 1l by 2l's. Right? And so, you know, once you have such a mixed volume construction, it is immediate that you have Logconcavity. But it is, sort of remarkable, right? Because, it's a purely combinatorial question having nothing to do with convex geometry or mixed volumes. And in fact, no combinatorial proof of this theorem is known. And the only known proof goes through mixed volumes, right? You would think if this is a combinatorial question, you could give a combinatorial proof, right? For example, by creating an injection between the sets of linear extensions with different ranks, right? But it doesn't seem that such a proof is or at least none is known. So the way I would like you to think about this theorem, it's a theorem in combinatorics. But really what this is an isoperimetric inequality for partially ordered sets, because it's one of these Alexandrov-Fenchel inequalities for mixed volumes, right? So you can hit this on a combinatorial problem and get a kind of isoperimetric inequality for combinatorial problem. And if you have an isoperimetric inequality, you can also ask, well, what is the solution of the isoperimetric theorem, right? The isoperimetric theorem would ask which partially ordered sets minimize ni if I fix ni minus 1 and ni plus 1, right? That would be the solution of the combinatorial question. Or in other words, you could ask, what are these diabolical bubbles, right, with these spikes? What is the analog of that picture for partially ordered sets? Right? And that is really an instance of the geometric question that we asked before. Okay, and I'm going to come back to this example at the very end and show you what the answer is, and show you why you might care about it. What does it say about partially ordered sets? Okay, so here is just a completely different type of application where you wouldn't expect this type of theory to come up. And yet you have these strange diabolical bubbles showing up in a very different set. All right, so let's go back. So I'm now going to try to explain to you with a very hand-wavy way what these equality cases look like and what they are. I'm going to be very vague, and I'm going to put down some definitions which I'm going to ask you to immediately forget. It turns out there are many equality cases, and they're a bit hard to describe, but I hope you will get the flavor of what is going on. So let's start with the cap bodies. Okay, so let's just think about the cap bodies just to get some intuition for what is going on. So the cap bodies, right, those strange bubbles, here I've drawn one with just one cap, okay? So they are an equality case in dimension 3, for example. They are an inequality case of the Alexandrov-Fenchel inequality, where the reference body M, that was C1, happens to be the same as K, and it's a cap body, and L is just a ball. Now, let's look at this. So remember, in the general inequality like this, M is fixed, and here you have KL, here you have KK, and here you have LL. So of course there would be a trivial equality case, which is if K is equal to L, then you of course have trivial equality, right? Because you have KKM, KKM, and KKM, right? So that would be a trivial equality case when K is equal to L, right? But here K is not equal to L for these cap bodies. But what you should notice in this picture is that K is equal to L in many directions. What do I mean by that? Let's fix a direction. For example, let's look at this blue direction. Let's fix this direction that goes off like this. And let's look at the plane, the hyperplane that touches this body with that normal direction. So this is called the supporting hyperplane. So I drew it as a line, but of course this is a two-dimensional plane in R3, right? I take a two-dimensional plane with this normal direction and I take it to touch the body. Now, what you will notice in this picture is if I take this plane over here in this smooth part of the body, right? And I look at the distance from the origin, it will be the same as for the ball, right? Another way of saying this is if I look at this part of the body, right, the round part of the cap body is exactly the same as the analogous part of the ball, right? The ball doesn't stick out in the direction where there is no cap. So there are many directions in which this body looks the same. The only places where these bodies look different is where you stuck a cap on. So if I take, for example, this normal direction over here, right, this normal direction, I look at the plane that touches the body in this normal direction. Well, in this direction, the plane will touch the cap body here at the point, right? But in this ball, you see there is no point. So if I draw the same plane over here, it will no longer touch the body. Right? So another way of saying this is, you know, in directions that are not normal to a cap, right? The two bodies are the same. The only directions where they're not the same are where they're touching one of the caps. The key point here is that here, the plane here where the two bodies are not the same are touching the cap at a corner, at a singularity. And it turns out that that's exactly what is going on here, right? So the equality cases of the Alexandrov-Fenchel equality are going to be like this. We're going to look at the reference body M, and we're going to identify a set of direction in which the reference body is not too singular. And in all of those directions, the two bodies K and L have to be the same. But there are going to be some singularities. For example, here, this point, this sharp point. And the two bodies don't have to be the same in normal directions to that sharp point. And because those directions turn out not to show up in this inequality. I mean, it is a strange thing, right? If you're not used to thinking about these objects. But if you want to take away the basic idea is that when M is not smooth, it's going to have some parts of the surface where there are very bad singularities. And those very bad singularities are invisible to the inequality. So the bodies can be different in those directions where the reference body M has a singularity, a bad singularity. And exactly what that means, we will have to define. But in all the nice directions, for example, this point over here is the point where the body is smooth, where the surface is smooth. And in all of the directions where the body M is smooth, K and L have to be the same. And this is the basic idea behind the characterization of inequality cases. So in the next few slides, I'm going to put up more precisely what this means in the case of polytopes and in general dimension. So that's going to involve some definitions. And, again, you should not try to remember these definitions. I just hope to give a little bit of a flavor of what they are. So let's think about polytopes. Okay, so here is the Alexandrov-Fenchel inequality. I see I already forgot a square. Has to be there, of course. Oops. Well, okay, I'll fix it later. There has to be a square there. We're looking at equality case. And remember, we are changing these bodies K and L, but these bodies C1 to Cn minus 2 are fixed, right, on both sides of the inequality. So the idea is going to be that these bodies in some way determine a set of directions. And in those directions, the bodies K and L have to be the same, more or less. But in the other directions, the bodies K and L can be different. Right? And this will characterize the equality case. So what are the good directions? They have this name. They are extreme in a certain sense. Don't worry about the notation, except that it only involves these reference bodies that don't change. So a direction is extreme if you take all of these bodies, which we're now assuming to be polytopes, and if the faces of these polytopes with that outer normal direction contain linearly independent directions. So somehow in directions where the faces of the reference bodies are sufficiently high dimensional, right, that they span sufficiently many directions, those are the good directions, and in those directions, the bodies K and L have to be the same. But there might be some directions, in fact, there always are for polytopes, where all of the faces of these bodies are too low dimensional. They don't span many linearly independent directions. For example, if you take a normal direction so that every single one of these bodies has the hyperplane with that normal direction touches them at a corner, then this will not be true, and those directions will not be extreme. And in those non-extreme directions, the bodies K and L can differ. This is going to be the idea of the characterization. So just to give an example, if all of the bodies C1 to Cn minus 2 are the same, they're a fixed body C, then a good direction corresponds exactly to the fact that this direction is normal to a face of this body of dimension at least n minus 2. Right? So in dimension 3, a good direction is normal to a face of dimension at least 1, which is an edge, which means that the only bad directions are directions that are normal to a corner, to a face of dimension 0. And that's exactly what you see here. You see that the bad directions are normal to a corner, and in those directions, the body can differ. So again, don't try to remember all of these definitions. I'm just trying to give a flavor of what's going on. So in 85, Schneider conjectured that these were the only equality cases, right? So that you have equality, again, with a square, if and only if the two bodies K and L I forgot to mention that there is another symmetry here, right? Remember, mixed volumes are translation invariant, right? So you have a trivial equality when K is equal to L. But you also have trivial equality when K is a translate of L because of translation invariance, right? Also, these inequalities are scale invariant. So if I rescale L, I also still get equality. Okay, so there are some trivial equality cases. It's when K is a translate and a scaling of L. But Schneider conjectured that the actual equality cases are when K and the translated L are not necessarily the same, but they're only the same in all directions that matter, which are these extreme directions. And in the other directions, they can be different. Right? And that's exactly what is going on. So let's give an example. So for example, what would this conjecture predict? In dimension 2, there are no reference bodies. In dimension 2, they just VKL squared greater or equal than KKLL. There are no reference bodies. In this case, all directions are extreme. So then K and AL plus V have to have the same supporting hyperplanes in all directions, which means they have to be the same. So in dimension 2, this conjecture predicts there can be no non-trivial equality cases, which is true. That's easy to prove. You don't need any fancy theory for this. But already in dimension 3, this gives you a lot of non-trivial equality cases. So cap bodies are ones, but cap bodies are not polytopes, right? But here is an example of polytopes. Suppose that your reference body is a cube like this. So what are the good directions? The good directions are directions that are normal like this to a face or that are normal to an edge of the body. The bad directions, the direction in which the bodies can be different, are exactly the directions that are normal to a corner. So if I take K and L to be this cube, but I've just here, what I've done is I've shaved off some corners of these cubes. You see these two bodies K and L are exactly have the same, they touch the same planes in any normal direction that's normal to a face, because all of the faces are still here, right? They also are the same in all directions that are normal to an edge, because you see all of the edges are also still here. The only directions when these bodies are different is if I take a direction which goes out like this from one of these short shaved off corners. But in the reference body, those directions are normal to a corner. And those directions are not extreme. They don't matter. So I just gave some example. You can shave off any of these corners in an arbitrary way and you would still get equality cases. Right? So here you see what this conjecture means. It's another example in the case of polytopes. So what did we prove? In the case of polytopes, we proved Schneider's conjecture is true. This conjecture is true, provided all of the reference bodies are full dimensional. Now, these bodies don't have to be full dimensional, right? For example, if I'm in R3, I could take one of these, I could take C1 not to be a full dimensional body. I could just take it to be flat. I could take it to be a disk, a two-dimensional disk at 3 dimensions. And the Alexandrov-Fenchel inequality would still be a non-trivial inequality in that case. But in that case, actually you get new equality cases that are not predicted by Schneider's conjecture. And this was actually known a couple of years after Schneider's conjecture was published. Ewald gave a counterexample to Schneider's conjecture when one of the reference bodies is lower dimensional. But as far as I know, there was never any conjecture about what these equality cases are. Okay. So it is hard, the higher dimensional, the ones where the bodies are not full dimensional, the degenerate equality cases, there are many of them, and they're a little bit hard to describe in the talk. So all I'm saying about them here is that there are many new equality cases when the bodies, they C1 to C2 are allowed to be flat, are allowed to be lower dimensional. But we fully characterized. As far as I know, there wasn't even a conjecture about what they should be. Well, we have a complete characterization of what they look like. But if you will, the main equality cases, where the bodies are all full dimensional, right, when they all have non-empty interior, are exactly following Schneider's conjecture. And I just want to talk a couple. I mean, the proof of this theorem is long, and I want to give some, at least one very, basic idea that appears in the proof. So, how do we prove such a thing? Well, I mean, we just do induction on the dimension. I mean, this is a classical idea, right? So what would you like to do, right? Suppose we have an equality case in dimension n, right? Then, let's take that equality case, those bodies K, L, C1, C-2. Let's pick some n-1 dimensional hyperplane in our n. And let's just project all of those bodies onto that n-1 dimensional hyperplane. Well, if we could prove that those projected bodies must be equality cases of the Alexandrov-Fenchel equality in dimension n-1, and we've characterized all of those equality cases in dimension n-1, then we know exactly what can be the projections of all these bodies in all of these, in all different n-1 dimensional hyperplanes, and then we can try to glue together this information somehow to form to derive the characterization dimension. Of course, the gluing is not obvious either, but in first instance, you just want to understand how to do induction in the first. So this seems like a great idea. I mean, everybody has seen, since they were in kindergarten, proofs by induction. I'm not saying anything deep here, it seems, right? But the problem is that this statement I'm making here is just not true, okay? And to see it, we just go back to the previous slide. Remember, in dimension n-2, there are no interesting equality cases, right? 2, you only have equality if k and L are the same up to translation scale. And here I have an equality case in dimension 3. Well, I mean, it's obvious that there are directions that I can project k and L and C on, such that k and L are not translates of each other, right? If I project in some direction like this, right, then the projection of k will be a square with a corner cut off over here. The projection of L will be a square with a corner cut off over here, right? These are obviously not equal up to translation scaling. Right? So, it is just not true what I said, right? I mean, it's a great idea, but it's simply not true that if you project the equality case in dimension n onto an n-1 dimensional hyperplane, you get equality case in dimension n-1, and you see it immediately in this case. So this seems to be a fundamental obstruction in this in proving such theorems, and the way we get around it is is a little bit surprising. The key idea here is a kind of resolution of singularities. And remember that I said is that if you try to just look at the proof of the inequality in the case where the bodies are not smooth, all of the objects in it become completely singular. And that singularity is very closely related to the phenomenon I just showed you, which is that the inequality, the equality cases are not stable under projection. So what we do is we do the following. We prove a theorem that looks like this. If you start with some equality cases in dimension n, it is not true that if I project those bodies onto an n-1 dimensional hyperplane, you get equality in dimension n-1. But what can I do? I can take one of these bodies k, and I can wiggle it in certain directions. I have some degrees of freedom. What directions am I going to wiggle it in? I'm going to wiggle it exactly in the directions that don't matter, right? Because in the characterization of the equality cases, the bodies are allowed to differ in non-extreme directions, right? So what I can do is I can take k. If I wiggle it in the directions where the bodies can differ, I don't change the equality cases, right? Or at least the ones we want to prove. So I have some degrees of freedom that I'm allowed to wiggle these bodies in without changing the set of equality cases. What we show is that if we start with any such equality case, we can find some wiggling of k, let's call it k tilde, such that after wiggling, the new sets of body do give equality if you project them onto a generic n-1 dimensional hyperplane. So after you wiggled them, then the problem somehow desingularized, and you can perform this induction. And that is the basic idea. And the miracle of this theorem is that, we can prove this theorem without understanding the equality cases, right? Because if we already knew what the equality cases are, if we proved the equality cases, this theorem would be trivial, right? Because the equality case says that k must be equal to a homostat of L in directions that are not this, right? So if that's true, I could just take k to, I could take k tilde to be equal to AL plus V, and this theorem would be obvious. But the miracle is that we can do this desingularization without understanding anything about the equality cases of these bodies. And that is a very basic step in the proof that is allowing you to deal with these very singular behavior of these equations. Now, even once you've done this, you still have to then take this information from all of these n-1 dimensional hyperplanes and glue them together to form the n-dimensional equality cases. And this is not entirely trivial either. And it becomes particularly difficult in the case when the bodies are lower dimensional. This is where these new equality cases, the lower dimensional equality cases, they arise because when the bodies are lower dimensional, you can take various equality cases in dimension n-1 and glue them together in non-trivial ways. And then you form new equality cases in dimension n. And that's a whole separate story that I'm not talking about. So this is really the most basic idea in this proof. And that's all I want to say about this talk, but it at least gives you some sort of flavor of the type of difficulties that are. So I just want to give in the last few minutes, let's get back to the to this combinatorial example. So remember, we have a partially ordered set, and we have these combinatorial objects, which is ni, right, is the number of linear extensions of this partially ordered set. such that the distinguished element X has rank I, right? It's the ith largest in the total order, the ith smallest in the total order. So remember that ni squared greater or equal than n minus 1, ni plus 1, this was just the Alexandrov-Fenchel inequality, right? Log concavity of this sequence was just a consequence of the Alexandrov-Fenchel inequality. So if you want to know when you have equality, all you have to do is take those polytopes K and L that Stanley constructed, stuff them into our main result, and see what happens. Now, it turns out you can, of course, do that. It turns out it's still not that easy because now you have some geometric information about these polytopes. But of course, in the combinatorial problem, you want to understand combinatorially what that means about the partially ordered set. You know, the conditions say something about the dimensions of the faces of certain polytopes. So now you have to translate this back to a statement about combinatorials, right? So this requires some work. But, you know, the only thing I want you to take away from this theorem is that it's possible, okay? So here is some characterization. You know, the only point of this, I mean, let's not get into what this theorem is actually saying. But, you know, the only point of this is that we can equivalently characterize equality, right, in the Logconcavity inequality by some condition that depends exclusively, you know, explicitly on the partial order that sits on this set. You can just, you know, if I give you any partial ordered set, you can compute this condition immediately. It's a triviality. So, you know, here is a combinatorial theorem. It was open for a very long time. You know, it's asked in Stanley's paper, what exactly are the equality cases for this inequality? But I just want you, when you see such a theorem, don't think combinatorics. Just think back to those diabolical bubbles, right? Those bubbles with all the spikes. Because this condition 3, whatever it is here, this combinatorial condition, this is all it is it's one of those bubbles, but in the context of partially ordered set. It's not exactly one of those bubbles. It's morally one of those bubbles, right? This is a partially, you know, this is a diabolical bubble for partially ordered sets. It's one of those strange equality cases, right? And it means something combinatorially in this set. So, you know, what can you extract? What information can you extract from this type of result? Right? So let's look at it for a moment. So one of the things you should notice here is that this is a byproduct of this proof. That, you know, if you have equality here, in principle, it could be the case that ni is twice ni minus 1, and then I plus 1 is twice ni, and then you would have equality here. Right? But one of the things this theorem says is that's not possible. So, one immediate consequence of this theorem is that this Logconcave sequence that you get for partially ordered sets, you know, a priori you might think maybe you can get more or less any Logconcave sequence this way, but that's not true, right? It turns out it cannot contain any 3-term geometric progressions. Okay? It cannot contain a sequence ni minus 1, ni plus 1, that each of them is twice the previous one or 3 times the previous. And if that is true, then the only way that the sequence can look is something like this. You know, first it can be 0 for a while. Then it must increase to its maximum in a strictly Logconcave way, right? In this region, you cannot have equality. Then you can stay at the maximum for a while. And then you can decrease in a strictly Logconcave way back to 0, and you can be 0 for a while. Right? And of course, you know, the picture could also end here, okay? I mean, you don't have to have every regime in this picture. But in general, it looks something like this. And this is a very strong constraint on the sets of Logconcave sequences that you can get, right? I mean, this is, you know, you can't just get any Logconcave sequence from this, right? You can only get Logconcave sequences that look like a certain way, which is a lot more information about the Logconcave sequences that arise in this example than you would get from the Alexandrov-Fenchel inequality. Moreover, you see there are these 5 regimes, the 0 regime, these 2 strictly Logconcave regime, the maximum regime, and another 0 regime. And the sizes of these regimes, they can be read off explicitly from this theorem in terms of the partially ordered sets. So if I give you any partially ordered set, that theorem will allow you to compute exactly the lengths of each of these regimes that you get. So, you know, this is I mean, it's surprising. At first, it's not clear what these bubbles are telling you about partially ordered sets. But once you understand what they're saying, they're actually giving you an enormous amount of information about the kinds of Logconcave sequences that arise and how they are controlled by the combinatorics of the partially ordered set. So just an example of these bubbles showing up in very different ways. So I think I'm at the end of my time. I will just say one word about this slide. Alexandrov-Fenchel inequality is one of the fundamental results in convex geometry. It turns out to be connected to many other areas of mathematics, both in the sense that it is directly connected, right? So like in the Stanley example, but also that there are sort of Alexandrov-Fenchel-like inequalities turn out to appear in many other areas of mathematics. For example, in algebraic geometry, these are inequalities for the intersection numbers of divisors. In Kähler geometry, where they live in the cohomology, the product of the cohomology. In combinatorial geometry, where there's very beautiful results, well, very celebrated, Avadi Prasito Katz recently, and various other areas. And the type of questions I've asked here make a lot of sense in those settings, and basically nothing is known. And I think, these questions are very interesting, whether the type of phenomena that I've shown you in this talk exists also in these other areas of mathematics. And I would really like to know the answer. But we have some sort of conjectures, but they're so speculative that I wouldn't necessarily trust. Of course, the case of general convex bodies is still, open in complete generality. We have a lot of theory for that. So there are some questions of geometric measure theory that are in the way. But I think that case, that should be resolvable in the next few years. But, I might be completely wrong about that. You can come tell me I'm wrong in a couple of years when we don't manage to do that. That's it. Thank you very much.
Thank you.
Let's thank our speaker. And are there any questions?
Yeah, I have some remark maybe.
Yes, please.
I happened to come across another application of the Alexandrov-Fenchel inequality last semester. It's the van der Waerden conjecture. So
yes.
Somehow, do you know about that? So
yes.
Somehow one can use so that too, yeah. One can use one can express the permanent using mixed volumes. Yeah.
Let me make a remark about this. And I should have said it actually. I mean, this is not. That was an omission. Mixed volumes. They are object defined for convex bodies, right? By this, right? So the volume of λ1. The volume of λ1 k1, right? So lambda n mkm is the sum of lambda I1 to lambda In of these mixed volumes. But actually, there is an analog of mixed volumes. I talked about algebraic geometry, Kähler geometry, etc. But there's an analog of mixed volumes in linear algebra, and they're called mixed discriminants. And they look like this. If I take the determinant of λ1 m1, right? Obviously, this is from its definition, this is a homogeneous polynomial, so you can expand it in terms of its coefficients. And these objects are called mixed discriminants. And they are analogous to mixed volumes in many ways, and they're closely connected to mixed volumes. Okay, so this is, you should think about this as the linear algebraic analog of mixed volumes. And mixed discriminants are highly non-trivial, so they satisfy Alexandrov-Fenchel inequality. Okay, same statement as for mixed volumes. This is easier to prove than the Alexandrov-Fenchel inequality, but it's not at all an obvious fact. And one can ask the same question there: what are the equality cases of the mixed discriminant inequality? And this problem has been solved completely by Panov. And our characterization of the equality case of Alexandrov-Fenchel looks very, very similar to the characterization of Panov in the lower dimensional case, in the case where you have lower dimensional bodies. But it turns out that mixed discriminants are much simpler than mixed volumes. And the reason they're much simpler is that there is no analog for mixed discriminants of these directions in which the bodies can be the same. So the only non-trivial equality cases for mixed discriminants arise when the matrices become rank deficient. And that's exactly the analogous to having lower dimensional bodies for the Alexandrov-Fenchel equality. So there's no analog of cap bodies for mixed discriminants. Now, in the application you're referring to of the van der Waerden conjecture, right, there is a representation of permanence in terms of mixed volumes. But actually, you can represent permanence in terms of mixed discriminants, okay, also. And that is really a better way to do it because the mixed discriminant inequality is so much easier to understand than the Alexandrov-Fenchel inequality. So in the mixed discriminant inequality, there, you cannot get the most interesting non-trivial equality cases, which are what's conjectured by Schneider, there's simply no analog of those for the mixed discriminant inequality. They don't exist. The only interesting equality cases there arise when the matrices are rank deficient. So, for that particular problem, it turns out to be simpler because it involves a simpler object. Whereas, for example, in Stanley's theorem about Logconcave partially ordered sets, this cannot, at least, okay, I haven't disproved it, but I don't believe that this can be expressed in terms of mixed discriminants. It's really a fundamentally mixed volume object. And so that becomes a much more difficult situation.
Thank you.
Yeah, you're welcome.
Other questions?
Hi, Ramon.
Hi. Hi, I'm here.
Just about the last comment, I never thought about it until you said this, but if you replace the matrices in the determinant by positive definite matrices, then suddenly the signs matter. And such polynomials.
Signs. Sorry, say this, the signs of what?
If the matrices M1 up to MM are positive definite, and the lambdas are positive, then the corresponding object you get is positive definite.
So this is when I say there's an Alexandrov-Fenchel inequality for mixed discriminant, the statement is that dmn R1 to Rn squared is greater or equal dmm, let's say R times, I'm just taking shortcut notation, right? So the script R is R1 to Rn, when m and R1 to Rn are positive semi-definite. Okay, so being positive semi-definite is a sort of equivalent to being a convex body, right? Yes. And you also take non-negative coefficients here in that case. So if they're strictly positive definite, that's like being a full dimension. That's the analog of being a full dimensional convex body, right? There's no kernel of these matrices. But the Alexandrov-Fenchel inequality for full dimensional convex bodies are all of these complicated equality cases that were conjectured by Schneider. But the mixed discriminant inequality can never be equality when the matrices are positive definite. So the only non-trivial equality cases of this inequality come when the matrices are positive semi-definite and they have non-trivial kernels. And in that case, there is some condition on how the subspaces of how the kernels of these matrices interact that causes you to get non-trivial equality cases. And this condition is very similar to our characterization of the equality case of Alexandrov-Fenchel for lower dimensional bodies when they're flat. But there is no, right? So when they're positive definite, there is never equality here. But in the Alexandrov-Fenchel inequality, when you have full dimensional bodies, you have many equality cases, right? So that's the sense in which the mixed discriminant inequality is simple. But if the bodies are not positive semi-definite, this inequality is false. I mean, this is just, right? I mean, you do need to assume that to have such an inequality. I don't know if that answered your question, but yeah, I mean, it is important to have this. Otherwise, you do not have such inequalities.
So in light of your last remark, so maybe like when you try to use Alexandrov-Fenchel to prove van der Waals, so maybe you can't use the inequality for mixed discriminant, because there I think the matrices are only assumed to be stochastic or something, not positive.
No. It works just fine with mixed discriminant. I mean, the proof of van der Waals only uses the mixed discriminant inequality. And that was, I mean, if you look in the paper of Egorichev, he says, I use the Alexandrov-Fenchel inequality, and then he writes down this inequality. So he just calls this the Alexandrov-Fenchel inequality for matrices. Right? And the permanent is just the permanent of a matrix S is just a mixed discriminant where you plug in here diagonal matrices with the rows that are where on the diagonal you have the rows of S. So these are positive, right? Because it's a stochastic matrix, so the entries have to be positive. You just take the rows, you put them on each row in a separate diagonal matrix. They are positive, right? Or at least or non-negative, and then you can apply this inequality, and that is really what is used in this proof of Egorichev. It's now. You can also represent the permanent of a matrix as mixed volumes.
And then you just
get the same inequality.
Even cubes,
maybe cubes. Yeah, you're right. Cubes. Sorry.
Cubes.
Not simplices. Cubes. and then you get the same inequality, right? But it works just fine with the mixed discriminant.
Yeah.
Of course, for that you only need the inequality. You don't need to understand the equality cases.
Thank you.
Of course.
Ramon, hi.
Yes.
Anyways,
hey, Emmanuel.
Hey, how's it going? How are you? Since this became a point of discussion, then I thought I'd use this opportunity, first of all, to say hi and say thanks. And also just to remark, I think for mixed discriminants, it's enough to assume that N is just one of these matrices, like let's say N is symmetric. So one of them can be just symmetric, not necessarily positive definite. Anyway, doesn't matter. This is an excuse to say hi to you. That's
it. Absolutely. You can take one of, not the reference bodies. You can take one of the two to be just symmetric. This is also true for the Alexandrov-Fenchel inequality. So for the Alexandrov-Fenchel inequality, rather than writing VKL C1 to Cn minus 2 squared, you could write it like this. Let me not use tilde because I used that for something else earlier, but let me call it K prime, greater or equal than V. Okay, now you have to V LLC, and then you get times what you get formally by taking the difference, right? So you get V KKC plus V K prime C minus 2 V K prime C. And now this is exactly like taking K, instead of taking K, a convex body, you take it to be the formal difference of two convex bodies, not in the same of Minkowski addition. It's a little bit confusing, but the formal difference of two convex bodies, that's exactly the same statement as the fact that here you can take M to be not just symmetric, not positive semi-definite. So these type of things have nothing to do with mixed volumes or mixed discriminants. They're general facts about hyperbolic inequalities. That if you have an hyperbolic inequality like this, then you can always extend it by making one of them a difference of two elements in the cone. These are. So if you had any such inequality in any area of mathematics, you would be able to self-improve it for free to get this type of behavior. But you're absolutely right, and it's great to see. So hi.
Thank you.
There are many general inequalities that follow from the Alexandrov-Fenchel inequality, right? For example, if I had more than two bodies, let's say I had 10 bodies, K, I could form this matrix Ki, Kj, C1 to Cn minus 2, form this matrix Mij. If I had, right, so if I have, and then you would get this inequality, the determinant of M times minus 1 to the, if Ij is 1 to L, minus 1 to the L is greater or equal than 0. If L equals 2, I've just written here the Alexandrov-Fenchel inequality. It looks like the determinant of something is negative, right, of a 2 by 2 matrix. But this is true for any L, right? So these are higher order inequalities. But these type of inequalities, again, follow from a formal argument from the Alexandrov-Fenchel inequality. So, a question I often ask from people who are not used to it is the Alexandrov-Fenchel inequality, you fix n minus 2 bodies and you only vary 2. That seems very special, right? I mean, that seems like something very special. But that's the basic primitive. And once you have such inequalities, you can iterate them in many different ways and get many different higher order inequalities. But this is something separate that is known how to do in various situations. But it doesn't just end there. If you wanted to understand the equality cases of these iterations, you'd have to understand the equality cases of each step and put them together. And that's
Other questions? So I actually had two.
sure.
Going back to the Khovansky-Tessier inequalities. So I don't remember I just looked up the only proof that I know, but is there a proof that uses these convex body arguments? Like, is there a way to
No. It goes the other direction. So the Khovansky-Tessier inequalities, when you apply them, so these are inequalities for Cartier divisors on projective algebraic varieties, right? And if you apply this inequality to toric varieties, then they will be equivalent so if you apply them to toric varieties, projective toric varieties, they are equivalent to the Alexandrov-Fenchel inequality for lattice polytopes, for polytopes whose vertices are on the lattice. And this actually gives you a way of proving using algebraic geometry the Alexandrov-Fenchel inequality, which was what Khovansky and Tessier were doing in the 1970s and early 80s. But that's just, but their inequality works for general projective varieties,
right?
And that's more. So you could think of the Khovansky-Tessier inequality as being strictly more general than the Alexandrov-Fenchel inequality. Okay. Now, as you know, remember I said something about the Alexandrov-Fenchel inequality that if you take nice bodies, there are no non-trivial. For example, smooth bodies, you get no non-trivial equality cases. This is also true of Khovansky-Tessier inequality. If you take ample divisors, there are no non-trivial equality cases, and that is used heavily in the proof. Okay, but if you go to Neff divisors, then suddenly you can get non-trivial equality cases.
Right.
And the analog of the questions I asked. So the fact that for ample divisors you don't get interesting equality cases. This is just the Hart-Lefschetz theorem. And now the analog of the question I asked here is if you look on Neff divisors, the Hart-Lefschetz theorem is not true. Right, the Lefschetz mappings can have a non-trivial kernel.
Right.
And what we did here is characterize that kernel geometrically. And so you can rewrite our theorem. Is just you can translate it literally into a statement about the characterization, a complete geometric characterization of the kernel of these Lefschetz mappings for toric varieties. You can rewrite this in the language of algebra.
Sure.
And then you might ask, well, can we do something similar for any projective variety? And we have in the paper some sort of conjecture about what is the correct formulation of such a thing. But whether it's true in any other example than toric varieties, I have no idea. This is an interesting question.
I'll take a look.
Yeah.
Also,
you said you have a second question.
Yeah. So the cap. When you add these cap, I mean, so both of those at least are. Suppose you start with a real algebraic variety, say a sphere, right? And you add the cone is the real locus of a singular algebraic variety, and you've glued them. I haven't thought about whether that gluing is algebraic or not, but do you know anything about whether this kind of this procedure preserves being an algebraic variety in anything more than dimension 2, if that?
Do you? Let me clarify one thing, which I think maybe that's not the question you're asking me, but the connection with algebraic geometry is not to view the surface of the convex body as an algebraic variety.
No, this was a question I had much earlier.
Okay, but just to clarify, I mean the connection. The analog of a convex body would be a divisor, right? It is right. It's not the surface itself. Okay, all right. I have no idea how to answer your question.
Okay,
but I think if you go to I think the answer. I mean,
higher dimension probably not.
Let me give you. I don't. How many singularities can an algebraic variety have? Does it have to be finite?
Arbitrary,
yeah. I don't know. I simply do not know. I haven't thought about the question.
Okay.
It does not naturally connect to the type of questions I talked about because that's not the relation algebra, but it is, of course, a question you can ask about. Well, I mean, you can ask the general question about which I've never thought. Which convex bodies have a surface that's an algebraic variety? I have no idea. But probably some people have thought about this question. It just isn't. But
at least the real locus of them is a convex body.
Yeah, well, of course, yeah. Well, I mean, there's also real algebraic geometry, right?
Right. Sure.
I have.
Okay.
I have. Now, the surfaces of these bodies can be very wild, right? Even for cap bodies, right? You can have a fractal pattern of caps sitting on top of the surface. Right. That's perfect because you can have countably many caps and you can arrange them in any way you want, right? So
yeah, you couldn't have that be algebraic, so that's fair.
Exactly. And this was the question, right? Then you have a countable number of singularities that form this
right. They could have positive
dimensions,
but you couldn't have a countable number like that. Yeah.
Okay. I see. So this can happen, and this is one of the main obstructions in this I skipped because I was out of time, but everybody can leave now. That's this picture over here that I took from the internet. Here you have a ball or a surface of a ball, a sphere, and this person who wrote this MATLAB package drew a circle packing on top of the surface, right? So you can just take a bunch of spherical caps, right? And then between them, you can put more spherical caps. Between them, you can put more spherical caps. And you can go infinitely off, and you get an Apollonian circle packing of the surface of the sphere, right? And that's a fractal. It doesn't even have to be fractal. There's no self-similarity really. It just means you have all scales, right? Now, if you started with any such circle packing, just take the center of every circle, and you can lift the point out of it in such a way that the cap that you get exactly touches the surface at the boundary of that sphere. You do this with every cap, and now you have a cap body with this sort of fractal or even worse pattern of spikes, right? And that's a perfectly respectable cap body, which is also an equality case of the Alexandrov, but it's very wild, right? The surface is very wild. And one of the main obstruction for general, now we do have we developed a whole bunch of machinery for general convex bodies, and for certain cases of the Alexandrov-Fenchel inequality, we already were able to characterize all the equality cases. But in complete generality, when you have many different bodies, C1 to CM-2, and they all look like this, but in ways that don't interact well with each other, that's really where the difficulty lies in the fact that these things can be very wild, and we don't have, our analytic theory is not yet good enough to be able to handle. It's completely orthogonal. The issues there are completely orthogonal to what I showed you for polytopes. And much of our theory for polytopes would go through if we had good, let's say, geometric measure theory machinery to handle some questions that arise of this today. So beware that you can have very, very, convex bodies. From the point of view of bodies in Rn, of sets in Rn, they're very nice. And their surfaces are Lipschitz. They're Lipschitz manifolds. But they're no nicer than Lipschitz. I mean, you can have very, very wild surfaces on convex bodies, and it really plays a role in this. So if this cannot be an algebraic variety, I don't know enough algebraic geometry to immediately see why not. But then you have the answer.
The singular locus has to be also an algebraic variety, which therefore has to have a
no way. Right, no way.
So, no, but that's a beautiful answer. That'd be a beautiful picture also.
It's not mine, but
well, no, I mean, a counterexample. That's a great counterexample. Other questions? All right, then let's thank the speaker again.
Thank you very much.
Thank you.
It was really great. Thank you so much.
Okay. Yeah, thanks. I hope it was comprehensible.
All right. Absolutely. It was great. All right. Thank you so much.
All right, guys. Yep.
Bye-bye.